Hello, my name is Bill Kraus, and I'm part of the Design Intelligence team at Adobe. And I'd like to talk to you today about a data model for automatically generating typographical layouts. Before I do so, I'd like to first touch on why automated generative design is important. Content authoring is based on the idea that more and better tools will enable creators. But this tools-only approach has its limitations. First, more tools come at the cost of complexity and have a potential counter effect when there are too many options available. Second, the migration to mobile and small footprint devices limits the available UI space. Third, creativity tends to be limited by the available tool set. There is a well-known adage that if all you have is a hammer, all the world's problems look like nails. And finally, while most people can appreciate good design, which is the basis of art and advertising, only a relatively small proportion of people can actually generate it de novo. There are several ways to address this problem. The first is tool intelligence, where tools and their functionality are contextually aware. The earliest and simplest forms of tool intelligence is tool modality, where only certain tools are available in a given context, and tool organization, where tools used at the same point in the workflow are grouped together. The second approach is through content intelligence. Here, the system provides content suggestions such as stylistic recommendations like color and font, asset recommendations as to which image or other asset is appropriate, and layout recommendations as to how elements should be aligned. In some cases, a design template is provided as a jumping-off point. Note that while there is some gray area between tool and content intelligence, the former enables the user to take a particular action, while the latter suggests an appropriate outcome for an action. Finally, there is true generative design. Here we flip the user-machine paradigm. Instead of the user designing and the machine making recommendations, the machine designs and the user makes recommendations. For example, imagine, based on some criteria provided by the user, the machine generates a set of initial designs. The user selects one or more of those designs, and the machine generates new variations based on those designs. This iterative process is repeated until the user finds an aesthetically pleasing design that meets their criteria. Note that for generative design, the design experience is less one of de novo creation than it is the exploration of design space and the curation of discovered designs. While the user is not actually designing per se, they still retain a sense of ownership and investment in a design because they have uniquely discovered it. Why focus on typography? Well, it turns out that typography provides an excellent playground for exploring generative design. If we think about it, all designs are built upon three pillars: semiotics, style, and layout. Semiotics refers to the semantic and emotional impact of the visual elements in a design. That is, many of the elements within a design represent concepts, archetypes, and symbols that elicit an emotional response and convey information. Style refers to the colors, fonts, line shapes, decorators, etc. that provide the look of the design. And finally, layout refers to the arrangement of the visual elements within a design, which controls the design's visual flow. It's not a stretch by any means to recognize that typography encapsulates all three. Typography clearly has a semiotic component, as the glyphs and shapes combine into words and phrases to represent ideas and concepts. Typography also exhibits style in the form of fonts and colors. And finally, typography exhibits layout, as the glyphs are organized into words and the words into phrases, and these glyphs and words are arranged relative to one another in the design. The next question is, why automate typography? Well, here are three rather simple graphic designs, all with a text phrase overlain on top of a single background image. Note how the use of creative typography can enhance the designs, making the designs more visually interesting. But unfortunately, these typographical layouts are often difficult for a user to create and maintain. For example, this simple layout requires a sequence of 6 separate transformations, which, even with grouping, may have to be repeated if the layout is moved or resized. But what if we could automatically generate aesthetically interesting, context-aware typographical layouts? Specifically, examples such as these, which include rotated and scale text, drop caps, and non-traditional alignments, all of which were generated using the data model I'm about to describe. This data model is the consequence of 3 insights. The first is that while there are typographical metrics unique to text, text elements are in essence graphic entities that take up space in a design. The second is that any typographical layout can be represented as a directed acyclic graph, where the nodes represent tokens and the edges represent the relationships between these tokens. Finally, the third insight is that typographical layouts are constructed through pairwise amalgamation, where a token is aligned to another token, and that group is aligned to a third token, and so on until the layout is built. These three insights allow us to represent typographical layouts as binary trees. Specifically, a directed acyclic graph can be decomposed into two separate binary trees, each tree representing alignments along one axis. Note that for a text layout in 3 dimensions, the directed acyclic graph would be decomposed into 3 binary trees. The leaf nodes in each tree represent the tokens in the text. Each node has a parent until we reach the root of the tree. The topology of the tree reflects the amalgamation sequence for building the typographical layout. And the relationship between children nodes are set by an alignment operator associated with the parent node. For the horizontal binary tree, the alignments are along the x-axis. For the vertical binary tree, they are along the y-axis. In addition, each node has an associated scale and rotation matrix. Now, if we expand the set of operators so that they specify transformations in 2 dimensions, then we can simplify the model even further into a single binary tree. Finally, by recursing down the tree starting at the root node, and ensuring that the layout of all children are resolved before the parent, we can determine the final transformation matrix for each token in the text. Note that while recursing down a tree is deterministic in that doing so will produce a defined layout, it is possible for the same layout to be encoded in different tree topologies. Here is a simple binary tree representation for a single line of text, aligned left to right. The tree typology is deep, and each parent node uses a left to right, baseline to baseline alignment operator, where each token is aligned to the preceding group. Note that while the leaf nodes correspond to words within the text phrase, those nodes can themselves represent the root nodes of binary trees where the leaf nodes are syllables or even individual glyphs. This recursive nature of the model, combined with a flexible set of alignment operators, allows support for a wide variety of layouts, including non-Western languages. Here are 2 examples that are more aesthetically interesting. In both cases, the tree typology is broad, employing several alignment operators as well as scaling and rotation. Note also, while leaf nodes typically map to text tokens, they can also represent empty space as well as graphic elements such as decorators or even images, which can be placed within the text flow. In addition, each node can be assigned a weight which reflects the visual weight of that node, and thus the importance of the tokens it represents, within the visual flow of the layout. These weight assignments may or may not correlate to the font used for that token, and can be assigned based on lexical or semantic properties of the text itself using natural language processing. One last point I'd like to make in regards to the weighting of text tokens. It's that the focus and intent of a design can be enhanced by correlating the token weightings with other assets in a design. For example, consider these 2 designs, both using the same phrase but having different background images. In both cases, the word which is given more visual weight in the design correlates to the subject of the background image. Note that this association can be generated in either direction. Deciding which text token is weighted can depend on the content of the other assets, or the content of the other assets can be determined by which tokens are weighted. This includes other text assets, where co-references across the text elements could be weighted more heavily. This example also highlights the relationship between the visual weight of individual text tokens and phonetic stress in speech. In both cases, a certain aspect of a phrase is emphasized and provides a cue to the viewer or listener as to how to interpret the original intent of the designer or speaker. So this begs the question, how are these trees constructed? Well, there are 2 ways. The first way is via programmatic tree construction. Here, incoming text is segmented into tokens. The typographical metrics of each of those tokens are measured, and each token is assigned a weight based on its relative importance. Consecutive tokens of the same weight are organized into a run. The set of runs that make up the text phrase are then used to construct an archetypal tree. Finally, this tree is modified based on a particular motif. What do I mean by motif? A motif is simply a typographical layout pattern. In this example, we have two motifs, each applied to two sentences. Notice how the same general layout is maintained regardless of the text. In the first motif, the last word is rotated respective to the preceding tokens, and those tokens are wrapped and right aligned. In the second motif, the text is staggered along each side of a central axis. Thus, each tree generating program is responsible for building a tree that reflects a particular motif, once it assesses that it can, as not all phrases can conform to every motif. The second way is through combinatorial optimization, using such techniques as hill climbing, simulated annealing, and genetic programming. The approach here is to generate many variations and then use a discriminator to search the design space and evaluate the results. Using this model, variations can be created for a given tree by rebalancing the tree or modifying the transformation operators associated with given nodes. Variations can also be created by swapping subbranches between trees. As long as specific constraints are met, such as the set of leaf nodes must be immutable, lest the text itself be altered, this approach can quickly generate a large variety of typographical layouts for even simple text phrases. Not surprisingly, preliminary work along these lines have demonstrated the necessity of a well-designed discriminator, as many of the generated variations are suboptimal, suffering from readability or overlap issues. But this approach has also occasionally generated aesthetically pleasing designs, and in any case, the key point is that this data model is conducive to the automatic search of typographical layout space. That concludes my talk on a data model in support of the automatic generation of typographical layouts. I'd be happy to answer any questions you might have.